The radical evidence, distributed memory and neural waves. Stakes first. If memories live as distributed patterns, then a sliver of the right cue should be able to light up the whole pattern. And when tissue is lost, recall shouldn't vanish by category. It should smear. Less detail, more noise, same gist. That's exactly what clinicians and labs keep seeing. Action. Start with pattern completion. You've lived it. A single chord, a whiff of cinnamon, the crunch of a certain gravel, and an entire scene unfolds. Faces, angles of light, a sentence you didn't know you stored. In controlled studies, tiny cues reliably trigger structured recall. In vision, presenting partial contours can provoke recognition of the full object before the missing lines arrive. In audition, leading intervals seed the brain to hear the song's continuation. In olfaction, the effect is louder. A simple ester can pull associated places and episodes on a short latency, and those associations survive damage that would cripple other modalities. Impact. Pattern completion isn't a party trick, it's a fingerprint. Hologram-like codes reconstruct from fragments. The brain's version runs on timing. When a cue aligns phases across frequency-tuned assemblies, constructive interference ramps up, and the large-scale attractor, the memory, snaps in. Meanwhile, something else is happening in the hippocampus and cortex. They split the labor. The hippocampus is a brutal librarian. It separates similar experiences during encoding, so today's coffee shop doesn't overwrite last week's rim. Cortex is the archivist. It generalizes and fills in. Recordings in animals show pattern separation, neurons indentate gyrus that diverge activity for near-identical inputs. Later, CA3 recurrent connections and cortical loops support pattern completion. We're entering a stored trajectory from a partial start. Human imaging echoes this. Lure items that are nearly identical to studied items drive different hippocampal signatures at encoding, but later retrieval lights up familiar patterns from minimal cues. Microstory. A patient lives with most of one temporal lobe gone after surgery for seizures. Names are hard. Daily details slip. But one afternoon, walking past a bakery, the smell of warm bread rises, and a childhood song rides in with it. Melody, the tinny radio, a cousin's red jacket, the exact chipped counter. The patient can't place the album, but they can hum the verse. The content is everywhere. The fidelity is down. That is the blur not delete signature in human time. Stakes. If damage reduces resolution, therapy should aim to boost precision, phase alignment, timing windows, targeted cues, not just brute repetition. And diagnostics should map how blur scales with lesion size, not chase a single missing file. This matches classic findings from the 1950s, 1960s lesion literature and modern imaging. Action. Distributed degradation shows up across species and methods. In rodent maze learning, lesion volume predicts performance drop better than location, unless you cut specialized bottlenecks. In humans, diffuse neurodegeneration, early Alzheimer's, vascular burden, shaves off detail before it deletes categories. People remember the event, but confound specifics. The restaurant, yes. The waiter's face, no. The table's position, off by a few feet. In language, anomia feels like phase drift. Phonemes are close, syllables swap. A neighbor word lands. None of this looks like a clean file gone missing. It looks like high frequencies lost first, then mid, then low. Impact. This gradient of loss maps neatly onto frequency domain coding. High frequency components encode edges, fine distinctions, timing precision. Knock them out with aging myelin loss, reduced inhibitory balance, or tissue death, and the system defaults to gist. That's not apologia, it's a measurable prediction. Interventions that restore high-frequency coherence should sharpen recall even when neurons are gone. Action. Now to oscillations. Gamma, around 30 to 100 Hz, often tags local feature binding, color with edge, pitch with onset. Theta, 4 to 8 Hz in humans, paces sequences and sets windows for when groups can talk. In episodic tasks, the two couple. Gamma bursts nest inside theta cycles. The timing of those bursts relative to theta phase carries information about order. In hippocampus, this phase code appears during learning and replays during rest and sleep. Wake an animal after learning a track and you'll see compressed sequences ripple off in the same order, often aligned to sharp wave ripples. Fast transients coordinating long-range communication. Disrupt those ripples and memory consolidation suffers. Stimulate on phase and recall can improve in controlled settings. Impact. That's not metaphor, that's a control knob. Stimulation of hippocampal theta during encoding enhances later recognition. Aligning stimulation to individual theta phase beats out random pulses. During sleep, coupling slow oscillations with spindles and ripples by auditory clicks timed to slow-wave upstates boosts targeted memories without boosting others. That's multiplexing in action. Action. Phase coding extends beyond the hippocampus. In sensory cortex, the phase of firing relative to local field rhythms can carry stimulus identity independent of rate. Two neurons with identical spike counts can encode different content by shifting when they fire within a cycle. Across distributed areas, cross-frequency coupling allows channels to coexist. Slower rhythms set the context window. Faster ones deliver content. Attention sharpens phase locking. Distraction smears it. When attention falters, gamma coherence between distant sites drops and feature binding errors rise. When attention is trained, coherence increases and the system resists noise. Microstory. A guitarist loses motor control in the dominant hand after an accident. The songs are gone. Months later, they start training the other hand. At first, it's clumsy. Then something strange happens. Progress accelerates in leaps. Old songs reappear faster than new ones are learned. The hardware changed. The song, the pattern, survived. The brain rerouted execution to new effectors while retrieving the same distributed memory with lower precision and rebuilding the high-frequency detail by practice, i.e., by sharpening timing. Stakes. Rehabilitation built on frequency and phase can speed remapping. Metronomes, rhythmic entrainment, breath pacing, and synchronized multimodal cues can act like reference beams, aligning distributed assemblies so the reconstructive wavefront has a cleaner path. Action. The connectome adds redundancy. Multiple pathways can produce the same output. Degeneracy, in the good sense. Knock out a node and traffic routes around it with extra latency. Learning then prunes and strengthens the new path, restoring speed and contrast. After stroke, speech networks recruit paralasional tissue and contralateral homologs. Training that emphasizes rhythm and prosody, temporal structure, often outperforms semantic drills early on. Why? Because timing reestablishes the interference pattern before content refines it. Impact. This is the opposite of a library. It's more like a stadium chant. Lose a section and the chant continues, softer and less crisp until the crowd adjusts. Your cortex is that crowd, pulsing in time. Action. Sleep shows the system stitching holograms at night. During non-REM, slow oscillations group spindles. Spikes replay compressed sequences. Hippocampus talks to cortex in bursts, cueing a memory with a related sound during the right slow wave phase. Selectively strengthens that memory the next day. Miss the phase, and the effect largely disappears. The cue isn't the file. It's the handle that aligns phases for replay. In motor tasks, targeted memory reactivation during slow-wave sleep can improve precision of specific sequences. In language, cueing vocabulary during slow-wave boosts, recall without contaminating uncued words. Layered holograms accessed by the right reference timing. Impact. This is the multiplexing prediction again. If multiple memories coexist in overlapping tissue, you need a way to call one without calling the others. Phase and frequency serve as addresses. Action. Critics push. Couldn't all this be explained by plain synaptic plasticity without wave talk? Sure, synapses change, but plasticity needs a teacher signal, and waves provide it. Temporal windows where spikes change weights more or less. Spike timing dependent plasticity is phase sensitive. Without rhythm scaffolding, which spikes count as together, you'd learn slowly and sloppily. With rhythms, you learn compositional structure efficiently, like separating instruments on different tracks and recombining them later. Microstory. A lab rigs up a closed-loop system. It watches a subject's hippocampal theta, then delivers a tiny pulse only at a chosen phase, while the person encodes pairs of pictures and locations. Later, those pairs are recalled more accurately than pairs encoded with pulses at random phases. Same brain, same pulse strength, different timing. The projector's interference improved reconstruction. Stakes. If timing is the handle, then diseases that flatten or desynchronize rhythms should hurt memory even when neurons survive. That's what we see. In mild cognitive impairment, gamma power and cross-frequency coupling often fall. In schizophrenia, gamma synchrony and long-range coherence are disrupted, and feature binding suffers. In depression, sleep spindles can weaken, consolidation dips. Interventions that restore rhythm,
Non-invasive stimulation, auditory entrainment, and pharmacology that balances inhibition show early promise in sharpening recall and perception. Action. There's one.
More clue. Graceful recovery after partial damage. After unilateral hippocampal resection, patients often show initial deficits in forming new memories of specific types. Over months, many improve. Cortex picks up weight. Contralateral structures adapt. Training that leverages multiple cues, visual, auditory, proprioceptive, accelerates this. Each cue carries overlapping frequency content. Together, they raise signal to noise, letting the system converge on the intended attractor despite fewer high-frequency components. Impact. The practical read is blunt. Don't just repeat content. Engineer cues that control timing. Beats, breaths, saccades, light flicker, and pair them with sleep. Use spacing that exploits natural rhythms of consolidation. Design rehab that treats memory as a pattern to be aligned, not a box to be found. Stakes. Because this isn't philosophy class, this is identity. When your projector glitches, your world blurs. If the evidence is right, you can tune the projector. And if the whole is in every part, then pieces of you remain accessible even when some parts are gone. Information physics, entropy, predictive coding, and the UI of reality. While those waves are doing the binding, another engine is running underneath. Compression. The brain isn't trying to store reality, it's trying to predict it with the fewest bits that still keep you alive. That's predictive processing. At every moment, higher regions send down guesses about what the next sensory input should look like. Lower regions send back only the differences. Errors. Minimize the error, and you've compressed the world. This framing aligns with predictive coding and active inference models developed from the late 1990s through the 2000s. Think of it as an information budget. Entropy is the cost. A disordered scene takes more bits to describe. Your brain pushes against that cost by learning regularities, edges, rhythms, voices, your front door squeak. The more you've learned, the fewer surprises you pay for. That's why expertise feels quiet. A chess master's board is low entropy because their model compresses it. A novice's board is noise. Here's where frequency earns its keep again. Efficient codes tend to live in frequency space because natural scenes have regular spectra. Lots of low-frequency gists, fewer high-frequency details. If you move information into a basis where most energy sits in a few coefficients, you save bandwidth. That's what JPEG does with cosine transforms. It throws away barely visible high frequencies and keeps the big structure. The cortex seems to do its own version, represent predictable backgrounds with slow rhythms, and deploy fast components only when needed. When energy costs spike, fatigue, illness, the system defaults to coarse predictions. You see the thing you expect and miss the small mismatch. Now layer in the UI idea. A desktop icon doesn't show you the machine code inside a file. It shows you a useful sketch. Perception works like that. Your constructs, color patches, edges, objects, faces are icons for survival-relevant regularities, not faithful reconstructions of physics. They're cheap to update, quick to act on, and always slightly wrong. That's a feature. A perfect rendering would be slow and expensive. Evolution bet on speed. If that sounds abstract, watch your brain handle lighting. In the checker shadow illusion, two squares with identical physical luminance look different because your model predicts a shadow and corrects for it. You see the corrected surface, not the raw measurement. The brain is subtracting expected illumination frequencies, leaving you with a stable surface icon. The error signal, what didn't match, drives a tiny update. You feel none of the math, you feel a world. Here's the trick that ties it back to holograms. Predictive coding needs a reference to compare against what you expect. Then it needs to interfere that with what arrives to reveal the difference. That's literally interference. The expected and actual signals superpose. Mismatches stand out as beats and phase slips. Circuits tune to those slips pass the errors up the hierarchy. Meanwhile, the matched portions cancel, saving bandwidth. Constructive for surprise, destructive for agreement. Entropy sits in the middle as a knob. When the world is volatile, new city, new job, your model raises its precision on error signals and lowers its trust in priors. You learn fast, your rhythms shift to favor exploration. Broader gamma bursts, looser coupling. When the world is stable, your kitchen,
You crank up the prior's weight, suppress error noise, and glide. Too much prior weight, and you hallucinate the expected. Too much error, and you drown in noise. The sweet spot is adaptive. Precision weights change by context, neuromodulators tune the gain, and rhythms set the timing windows to catch just the right differences. Get this. Pain offers a stark example. Chronic pain often reflects a model that predicts threat from benign
Inputs. The system assigns high precision to priors like "this movement hurts," so ambiguous signals get interpreted as danger. Therapy that changes prediction, graded exposure, attention training, literally shifts precision settings. Entrainment, breath pacing, and slow interoceptive rhythms can downweight error noise so new priors can take hold. You're editing the interface. Why call perception a UI? Because the same scene can render differently depending on your task. If you're catching a ball, you see trajectories in time to contact. If you're painting, you see gradients and edges. The underlying photons are the same. The chosen code, what frequencies matter, which errors get promoted, changes. Task demands retuned coupling between areas. Attention changes phase relationships. The interface reconfigures on the fly. This is also why illusions teach us more than veridical scenes. They expose the priors. Hollow masks look convex because face priors are heavy. Shepherd tones rise forever because your auditory model collapses pitch into a loop. The checkerboard fools you because your luminance model assumes shadows. In each case, the error signal is weak, the prior is strong, and your UI prefers the cheap explanation. Notice the survival angle. An organism that compresses effectively can act sooner and learn faster. It can assign precious spikes to the unexpected and ignore the rest. Sleep then sweeps the day's error signals into long-term changes, consolidating useful priors. Dreams might be the offline UI stress test, running the model without sensory constraints, probing edges, stitching stories to keep the generative code coherent. One caution before we drift into quantum land. None of this requires spooky physics. The holographic in our story is signal processing, distributed frequency codes, interference, and prediction error. It's non-local within tissue, not non-local across space. Decoherence is brutal in brains. We're not positing long-lived quantum states holding your childhood. We're saying your cortex behaves like an efficient codec with a great UI, built from rhythms and synapses. So when your projector glitches, trauma, sleep loss, disease, watch what fails. Precision weighting skews, rhythms desynchronize, and priors misapply. The UI flickers. Fix the timing, tune precision, feed better cues, and the picture steadies. That's practical hope, not mysticism. You can edit your interface by training the code that predicts it. Glitches in the hologram, trauma, hallucinations, and reality drift. When timing is the handle and priors are the code, you can guess what failure looks like. Gain turned up too high, phases slipping, and the UI filling in what isn't there. Trauma shows the loud version. After a blast or assault, the memory doesn't just strengthen, it saturates. The system stamps a high-precision pattern. Sound, smell, posture, light angle. So hard that any overlap in frequency space triggers completion. A car backfires, and the entire scene reconstructs. Body locks, breath spikes, the old room overlays the current street. The projector isn't broken, it's overconfident. Stakes here are human. A veteran sits in a diner. The hiss of the kitchen matches the spectral band from a generator overseas. That slice is enough. Interference pulls the full pattern. The diner dims into a checkpoint. The brain's job is to pick survival-relevant icons quickly. After trauma, the weighting tilts toward threat, and the overlap needed to complete the pattern shrinks. This is PTSD as overstamped interference. High gain, rapid lock, little tolerance for mismatch. Actionably, therapy targets precision and timing. Exposure with safety cues teaches the system to reweight error. This hiss isn't that generator. Breath pacing and slow exhale recruit vagal rhythms that widen timing windows, so cues arrive in a calmer phase state. MDR times saccades into a bilateral rhythm while recalling fragments. Critics debate mechanisms, but the practice manipulates timing, arousal, and cue structure, exactly the levers a frequency code would respond to. Over sessions, the intrusive pattern loses high-frequency snap. The same cue no longer detonates the full scene.
Hallucinations sit on the other side. Priors outrun data. In psychosis, the projector fills from expectation with little constraint. Auditory cortex runs hot. Speech, like rhythms in the brain's own activity, get misattributed as external voices. If gamma-theta coupling goes off and top-down precision gets oversized, the system promotes internally generated patterns as if they were error signals. You hear the model. Antipsychotics dampen dopaminergic gain on precision. Cognitive therapy trains reality testing. Slow down, seek mismatches, retune weighting. Get this, everyone hallucinates a bit. Close your eyes in a quiet room. Watch swirling phosphenes. That's cortex idling, generating patterns with no input. The difference in illness is calibration, without tight phase.
Coordination between areas. The UI can't pin icons to stable causes. The world breathes unnaturally, meaning slide. Deja vu is a tiny, mostly harmless glitch. Faulty pattern completion from frequency similarity. A current scene partially overlaps a stored pattern. Temporal rhythm, spatial frequency layout, and the hippocampus biases toward already seen. The tag for familiarity fires before the tag for source. You feel the click of completion without a file to attach. It passes because the system quickly discovers the mismatch and downweights the prior. Dreams are sanctioned glitches. Offline reconstruction runs without anchors. During REM and NREM transitions, the brain rehearses, stitches, and stress tests the generative model. While plots aren't mistakes, they're probes. The model blends frequency components from distant memories, trying new alignments, meaning get stitched from noise. Wake during the wrong phase and you carry a residue. Sleep inertia, a temporary desynchrony where priors feel sticky and inputs lag. Migraine aura offers a window into how sensitive timing is. A wave of cortical spreading depression sweeps across visual areas, temporarily altering excitability. Edges crawl, zigzags appear, blind regions open and close. It isn't in your eye. It's the projector's spatial frequencies falling out of register as excitation and inhibition slide. The UI struggles. The world looks unstable. Psychedelics push timing and priors deliberately. Lowered integrity in high-order networks, loosened precision on predictions, and increased entropy in spontaneous activity let bottom-up data flood in and priors soften. That's why colors bloom and boundaries melt. Therapeutically, the window can allow stuck patterns, like trauma stamps, to be rewritten when paired with safe context, music as a pacing scaffold, and trained guides. The risk is drift. Without structure, the system can encode noisy associations. Integration practices, sleep hygiene, breath, movement, schedule, help relock phases. Clinical evidence is emerging, but still developing. Anxiety is a chronic version of misweighting. The system assigns high precision to uncertain threats. Harmless cues complete into danger patterns. Attention narrows, gamma locks onto the wrong features, and you miss broader context. Breathwork widens interoceptive windows. Aerobic movement resets neuromodulators. Rhythmic practices like coherent breathing or synchronized steps act as metronomes for the projector. Over weeks, the UI stops painting hazard icons on every texture. Microstory. A barista hears the whir of a grinder and feels a surge of dread. Months earlier, that exact spectral whir overlapped a traumatic scene. In therapy, they pair the sound with new anchors, a counting rhythm, warm light, a friend's voice. At first, the old scene still tries to load. With repetition, the timing and context shift. The whir stays a whir, the projector learns a new completion. Alien abduction experiences during sleep paralysis. The model wakes before motor systems and proprioception do. With no movement feedback and a heavy prior for presence in the dark, the system completes a presence icon from interoceptive noise. Education alone, your projector is mistimed. Plus, sleep positioning, regular schedules, and phase reset strategies can reduce episodes. The dark edge is depersonalization and derealization. The UI's contrast drops. People report feeling like cardboard as if behind glass. That maps to hypoconnectivity between interoceptive areas and narrative networks. Low precision on body signals. Over-reliance on abstract priors. Treatment raises signal from the body. Temperature shifts, breath holds, cold exposure, paced movement, while reducing ruminations over coupling. Reality regains weight as timing between systems tightens. So glitches aren't random weirdness. They're lawful miscalibrations of gain, timing, and prior weight, which means they're trainable.
Phase can be reset, precision can be tuned, cues can be tamed or retagged. And the same tools that reconstruct a memory from a fragment can help you unhook a fragment from a memory.